Whiff-Whaff, a refined and innovative reinterpretation of the classic game Pong. Whiff-Whaff takes its name from the historical term for ping pong, giving the project a sense of tradition while presenting a modernised and enhanced experience. Our design introduces a central dynamic obstacle, represented by the red square you can now see on the screen, which travels the playfield and rotates with each cycle. This feature adds strategic depth and requires players to adapt to their timing and positioning. To ensure clarity in the gameplay, Player 1 and Player 2 are distinguished by red and blue colour schemes. The control buttons were also repositioned while maintaining their original input to provide a more ergonomic and intuitive user experience. Additionally, all wiring was neatly secured, ensuring a clean, organised and professional presentation of the hardware. I will now present a short clip of the gameplay. The footage has been edited to provide a clearer and more engaging viewing experience, highlighting the core mechanics and the unique features of Whiff-Whaff. By focusing on key moments, the clip showcases how the dynamic central obstacle, player interactions, speed increase of the ball, and overall flow of the game comes together to create an engaging and enjoyable game. I'm now going to give a quick code overview on how Whiff-Whaff works. I'll mainly just be giving brief pointers on each of the files, what they do and why we have them there. There'll be a more in-depth code review done by my teammate Aayan later on in this video. The main gameplay logic is in this file here called main C. This file defines the paddles for both players, the ball, the scoring system and the moving obstacle. It stores all the positions, speeds and scores, and also finally it runs the main game loop. For graphics we use two files, Sprite C and Sprite H, which you can see here on the left of your screen, which I'm hovering over with my cursor. Sprite C contains the actual pixel data for the red, blue paddle, the ball and the obstacle. As you can see we have them named here. The red square obviously is just the obstacle. All of this comes from the included .inc files, which you can see here on the left of the screen I'm hovering over. We have one for each, the ball, red and blue paddle and the obstacle. These just store raw pixel values, which the LCD can then draw. Sprite H, which you can see now on your screen, just declares all these arrays so the rest of the program can use them. The screen drawing then is handled by display C and H, which you can see here as I hover over them. These files provide all the graphics functions we use in the game. Functions to draw pixels, fill rectangles, place images and draw text, such as when you load into the game, you'll first see the name of the game Whiff-Whaff and press any button to start. That's why we use these functions. So overall, main C handles the game logic, Sprite C holds the graphics data, and display C handles communication with the LCD. Together these files create a complete embedded game system running entirely on the microcontroller. Now, I will hand you off to my teammate Aayan, who will give you a more technical insight into the code.
Hi, my name is Mohammad Aayan. I'm taking over from Shane. I'm going to be briefly explaining the three C files, display.c, main.c and sprites.c. Starting off with the lines 1 to 5, basically just the includes for the font, display, screen width, screen height. Moving on from 9 to 25, basically just helper functions like the tiny custom string length function and the CS low, CS high, the control chip select pins. Moving on to the begin display, 33 to 42 at the start. It just enables the GPIOA, then it configures PA3 and PA4, PA6 to the output chip select data and the data / command. All set up by modder, line 43, the SPI, that basically just sets the SPI 1 to so it can talk to the TFT. Moving on from line 45 to 55, it's just a reset dance. Basically make sure the display starts consistently. Lines 56 to 63, It's basically just the basic startup commands. Line 64 to 103. Starts off with frame rate, then goes into inversion mode, memory access mode, color mode. The values come from the display chipset datasheet. Moving on to 104 to 109. Turning on the display. I'll show you here. Turning on display, and then ready to receive pixel data. Then the screen is active. The final step on this is to clear the display. Basically, just blacks out the screen. We move on to pin manipulations like the reset low, reset high, CS low, CS high, DC low, DC high. The reset low, reset high is a PA3 to make it low or high. This CS low, CS high basically just enables or disables the SPI chip and selects PA4. Then DC low, DC high switches between command mode, data mode. Moving on to in SPI, basically just configures the SPI pins, PA5 to the clock, PA7 to data to display, alternate functions at 0. Also does master mode, 8-bit data and clock idle high. Then finally drains the SPI buffer. Moving on to transfer SPI 8 and 16. Basically they just wait for the transmit buffer to be available using the SPI 1 arrow SR, and 1 is smaller 7. The 16-bit version writes directly to SPI 1 to the DR. Commands and data basically over here. They're pretty important. The display decides how to interpret each byte based on the DC. If it's 0, it's a command byte. If it's 1, it is data byte. When open to open aperture, the display only draws inside the specific rectangle. It's every primitive drawing function uses this basically. The fill rectangle uses an open aperture, then sends the same color for all pixels. It's simple and fast. Put pixel is a mini rectangle, a 1x1 rectangle. Then put image draws an image. The steps for it just supports flipping horizontal and vertical. The draw line functions and its helpers is to implement the line algorithm. The draw line chooses which version to use. The draw line low slope or the draw line high slope, which is the shallow slope or the steep slope, and then these functions repeatedly call put pixel. The draw rectangle, the helper there, sorry, first. The draw rectangle calls the draw line 4 times. Then the draw circle and the fill circle. Draw a circle here and the fill circle over here. Basically, the draw circle draws the perimeter. The fill circle draws horizontal lines, basically to fill the interior. It includes safety checks to avoid off-screen drawing. Print text. Print text just draws the 5/7 font. Steps for each character basically just look up. Number 1 is just look up character bitmap. Number 2, build temporary pixel buffer. 3, fill it with the foreground or background color. And then 4, call the put image to draw it. Moving on to print text 2, basically same idea, but each pixel becomes a 2x2 block. Print number and print number 2 are also basically the same as each other. They convert a 16-bit number to into a 16-bit number to a string manually, then prints it using text functions. RGBT to world converts the RGB 888 to RGB 565, displays the RGB 565 format basically. The drawline low slope or the drawline high slope, just implementation for both slope cases. Put pixel, high slope, then put pixel basically. Clear is what I'm getting at. clear. Basically, just fill a rectangle, just clears the whole thing, blacks out the screen when the game's finished. Now, moving on to main.c, starting off with the includes and the screen game constants all over here. All over here. Moving on to the MCU headers, API, display API, standard stuff like libraries, text, fixed sizes, and the UI layout. Then the global game state over here, like the initial paddings, positions, scores, ball position, velocity, like that. Then we are going to move down to the make. That's all the stuff here, first of all. Then moving down to the make obstacle sprites, builds 20 by 20 in RAM images, solid red square or diamond for the object. Uh, yeah, wait for buttons is basically a busy wait. First waits until any four buttons are pressed, then until they're all released. The buttons are on PA8, 11, PB4, and PB5. Draw score clears it basically just clears the strip at the top and then draws a score blue on the left, red on the right, and then horizontal barrier line below. Uses the display helpers like the fill rectangle or the print number one or the print number two. Reset round. It's not really showing the snippet header, but typically it recenters the ball, reset speed, all that stuff. Moving on to windscreen. Clears the screen, shows a winner banner, red or blue, depending on who wins. Prompts to play again. That's and waits for a button to be pressed. Then moving on to the main system. Basically, the system bring up title screen, and then the game loop. System. Right. So we'll go on to the while loop first. The main game loop. Basically, each frame reads an input. It updates, draws the paddles, draws obstacle, moves ball, collision, scoring, draws ball, and delay. Basically, just reads the inputs. PA 11 left, PA 8 right, PB4 left, PB4 right for player blue on the top. Then it proceeds to go on and draw the paddles. Erases the rows back to black, then draws colored rectangles using the RGB2 world. Moving on, obstacle spawn and all that stuff. When inactive or on spawn random sides for the obstacle, and it just moves across the screen. It erases the last position, advances, potentially deactivates if off screen, and then draws either a diamond or a square. Moving on to the ball, clears the old ball, and then the longer the ball is on the screen, the faster it gets. Yeah, it has higher velocity while touching vertical edges. Basically, um, paddle bounce. Yeah, basically the the y velocity is flipped from the paddle, and the x velocity is set to hit the position, so the edges deflect off more. The obstacle bounce. If the ball overlaps with the obstacle, the 20 by 20 region, it flips both the x and y. Simple reflect, goes back, hits and goes back off. The scoring system now. If the ball goes above the barrier line for each side, the opposition gets a point. Hardware. Uh, yeah, just basically the hardware and the draw ball. To draw the ball in frame control. It renders the ball as a small white rectangle, and delay for like approximately about 7 milliseconds for pacing. Then the hardware configures the system tick to tick every millisecond, sets the system clock to flash wait states, and busy wait time milliseconds advanced by a couple whatever time. This also the small GPIO helpers to set the pin mode and sorry, pull-ups. Then sorry, sprite.c, basically it's just the sprites. It just says it's just the sprites uh, for the paddle sprite, blue and red, boss sprite. It just declares a constant array of 120 values in the flash. That's basically it. And all the sprites are basically similar, causing from here as well. So that's basically it for all the C files. Thank you.